Hi everyone, Mrs. Pesic here.
And Miss Bella here.
And we're looking at section 1.3, transforming linear functions. The objectives are to transform a linear function and to solve problems involving linear transformations. In lesson 1.1, you learn to transform functions by transforming each point. Transformations can also be expressed by using function notation. So if you wanted to do, for example, horizontal shift of absolute value of h units, you would input the input value changes. So f of x would become f of x minus h. If h is greater than 0, so you'd have like x minus 3 or x minus 5, that's going to be moving your function to the right. If h is less than 0, like x minus a negative 2 or x minus a negative 4, which would be x plus 2 or x plus 4, that moves your function to the left. And then if you wanted to have a vertical shift of absolute value of k units, we're focusing right here now, then we have the output value is going to change. So the f of x plus k would be your new function. If k is greater than 0, it moves up. If k is less than 0, it moves down.
Two more transformations that we'll be using are the reflection across the y-axis. So again, remember we talked about if you're reflecting across the y-axis, that means that you kind of be folding your paper right here. That means that the input, the x's are going to change. So a point that was here on the right is now going to move over to the left, and from the left would bounce over here to the right. So when you're doing across the y-axis, you're going to change the x and plug in a negative x, and those lines will be symmetric about the y-axis. So that would be the line of symmetry you could fold it on. If you reflect across the x-axis, so we'd kind of fold our graph in half right here, a point above will come down below, a point below will come up above. So the output, the y values change. So you're actually going to put a negative out front of the entire function, because remember, f of x is just a different way to write y. So we would make everything in the function negative, or opposite sign of what it has. So these lines would be symmetric about the x-axis. Just a little helpful hint on how to remember what these are. The difference between vertical and horizontal translation. So if you're going to add to the y value, so add to y, that goes high. So that will move it up and down. If you add to the x, go left. Again, kind of going back to this part up here. So technically, usually if you see like something that would be like x plus 2, that's really going to be x minus negative 2. So that's moving it to the left. So that's why the hint says if you add to x, you're going to go left.
Okay, so let's take a look at example 1. We're translating and reflecting functions. So let g of x be the indicated transformation of f of x, and then you're going to write the rule for the new function, which we're going to call g of x. In this case, the original function f of x is x minus 2, and we want to have a horizontal translation that goes to the right 3 units. So in order to do that, our function g of x, if we want the function to go to the right 3 units, we're going to take our original x right here, okay, and we are going to have to add or subtract 3. Well, in this case, since we want it to move to the right, we need a minus 3. And then don't forget, we still had the minus 2 from right here. So we get x minus 3 minus 2, which is the same as saying that g of x is equal to x minus 5. So let's see how that looks on our graph. So our original function is right here in blue. This is the line f of x equaling x minus 2. You can see that the slope is 1 and the y-intercept is a negative 2. And we wanted the function we wanted this original function to be shifted to the right 3 units. So it is sliding over 3 units to the right. So in other words, this point which was at 2, 0 is now over here at 5, 0 and so forth. And that means that our new function, which is g of x equaling x minus 5, gives us that graph. Slope is still 1, y-intercept appears here at negative 5 now, and so on. So that's our function g of x.
Let's try another example of doing that. This time we're going to have to actually come up with our f of x equation ourselves, and then we'll do the transformation. So for this one, we have a linear function that's defined in the table, and we want to reflect it across the x-axis. So my first step here is I have to write the rule or the equation for f of x in slope-intercept form. Now, remembering slope-intercept form, that's the same as y equals mx plus b. Again, in this case, we have that m stands for my slope, and that B stands for my y-intercept. Since we have some values in our table here, let's figure out what the slope, the m value, is first. Remember, we calculate slope by taking y2 minus y1 over x2 minus x1. So I'm just going to choose my first 2 points here. So I'll end up with 1 minus 0 over 0 minus negative 2. Or I'll end up with a slope of 1 over 2. Remember, that becomes positive 2 down there. So my slope is 1/2. So start building my equation here. To find my y-intercept value, that b, remember, a y-intercept is where it crosses the y-axis, so it's always 0 for your x comma something. So my table actually nicely has that point right in there for me, so that must be at 0, 1. So to finish off my equation here, I know my equation is 1/2 x plus 1. Now we can go on to step 2 and actually do the transformation. So we were asked to write the rule which would reflect it across the x-axis. Again, if we're going across the x-axis, so if I think about a graph, I'm folding on the x-axis, so a y value up here would come below, and something below would come above. So you're actually going to change every y to negative y, or every f of x to negative f of x. So to find my new equation of g of x in this case with the transformation, I'll say that g of x is equal to negative of the entire equation I just had for f of x, which was right here above. So negative times, or to the quantity of 1/2 x plus 1.
And we can write, I mean, up here we can write this as, this function was f of x equaling 1/2 x plus 1, right? So that was our original function, and now the reflection is just the opposite of that.
So we'll distribute this through just to clean it up a little bit, so we can end up saying that g of x is equal to negative 1/2 x minus 1. And if we wanted to take a look at what those graphs would look like, I just have to scroll down here just for a second. I could pull that up for us. There's what our two graphs would look like. So you'll see in this case that the original one is going to be, colors are a little backwards here, but the original graph in this one is in red. So that's the 1/2 x plus 1, so we're highlighting it in green. That was the original graph that we got from plotting those points. And now in blue, this is, so, well, because I typed them in backwards.
Oh.
So this, let's just rewrite this. This one is really f of x. And we'll use black. This is really g of x. That's just when I put them on the graph for us to see. Okay, so you can see that they are a reflection in this case over that x-axis.
Okay, so stretches and compressions will change the slope of a linear function. If the line becomes steeper, the function has been stretched vertically or has been compressed horizontally. So if the line becomes flatter, then the function has been compressed vertically or stretched horizontally. So let's start off by looking at, it's easier to start with looking at the vertical. All right, so let's look at the vertical side first. Vertical, if we have a vertical stretch, then we're just going to multiply our function by whatever we want to stretch it by. So if we want to have a vertical stretch by a factor of a, we're just going to multiply our function by a. And if a was greater than 0, that will be a stretch. If a is greater, if a is greater than 1, that will be a stretch away from the x-axis. But if we multiply our function by some value that's between 0 and 1, that's going to be pushing all of the values towards the x-axis, so that's going to be a compression. So in other words, if we compared, let's say compare three functions like f of x equaling x, f of x, or I'll say g of x equaling 2x, and let's say h of x equaling 1/2 x. This one here would be a vertical stretch, and this one here would be a vertical compression. Sure. So let's take a look at the graphs of those. So there's f of x equaling x, our original function, and then if we have f of x equaling 2x, we can see that that's vertically stretched. Things are getting pulled away from the x-axis. All right, and then if we have that last function, f of x equaling 1/2 x, which we can type in as 0.5x, you can see these values have been pulled towards the x-axis from the original. Did I just do something? Was that me? Okay, so these values on the original are being pulled towards the x-axis to get that compression of f of x equaling 0.5. 5x or 1/2 x.
Okay, so now we're going to go back to the horizontal. This one is a little bit not as intuitive as you would think for a vertical. Vertical is nice, you just multiply by what you need. When you're doing a horizontal stretch or compression, we're going to be changing the input and changing the x values because we're moving it away from the y-axis. However, the way that we do this is going to be a little bit different. We're actually going to take the reciprocal of what value we want to stretch or compress it by. So we're actually going to multiply just the x portion by 1 over b, where b stands for how far you want to stretch it. So if b is greater than 1, you're really going to be stretching it away from the y-axis like you kind of see in the diagram here. If the absolute value of b is between 0 and 1, it's actually a compression. However, that means in the function here, it's still going to be the reciprocal of 1 over b times the x. So really, let's graph this one too, because I think that's really the easiest way to understand this. And I'm going to kind of jump ahead and I'm going to look at a quadratic function just because it makes it a little more sense than using a linear function. The rule still is the same, but it just makes it a little more clear. So if my original was f of x equals x squared, let's look at what would happen if I typed in, again, just changing the x, so square still stays on the outside. We'll put a 2x in there, and then we're also going to test what it would look like if I put in a 1/2 x and then square that quantity, just to kind of see the difference here. So again, let's get a new graph page here. And so let's start off with just x squared. So here's our basic parent function we talked about in an earlier lesson. Now, I'm going to put in, again, just changing the x. Just the input.
Yes, you got to have the 2x in parentheses before you square. Now, what do you think is going to happen? Do you think that's going to be a horizontal stretch or a horizontal compression?
Right, so coming closer to the y-axis or farther away. If it was like vertical, we would think, well, it's going to get bigger and farther away. However, look what happens. So by putting in a 2 with the x, actually it pushed all of the values closer to the y-axis. So that's actually a compression, even though we put a 2 in, a number larger than 1. So that's a horizontal compression. Okay, now let's compare that to if we put in a 1/2 in there with the x. So I'm going to go back, I'm just going to add it to the same page. Again, in with the x, so inside the parentheses, I'm just going to put 0.5 in. 0.5x, close parenthesis, and then square that quantity. Again, pink was my original color here. Notice what happened in orange. The orange is pulling all of those pink points farther away from the y-axis, and that really was a horizontal stretch in that case. So only when you're dealing with the horizontal, so changes along the x's, the x values there, that's going to be a little bit different than what we would think. So again, going back to our notes page here, we just looked at this one in green was actually a compression, and this one in blue was actually a stretch. So whenever you're dealing with changing it along that, the x's, you want to put in the reciprocal of what you're using.
Okay, so a helpful hint, these don't change. The y-intercepts in a horizontal stretch or compression will not change. So if you're stretching something horizontally, the y-intercept's going to stay the same. Same thing if you're going to have a horizontal compression. But if you're going to have a vertical stretch or a vertical compression, then the x-intercepts will not change. All right, let's take a look at another example. Example 2, stretching and compressing linear functions. Let g of x be a horizontal compression of f of x equaling negative x plus 4. So we're using this function as our original function, and we want to have a, oh, I pulled it up, I tapped it. We want to have a horizontal compression by a factor of 1/2. So we take our function, we're going to call this g of x, and we're going to take our original function, but instead of just putting x here, we want a horizontal compression of 1/2. If I just put in 1/2 x right here, that's going to give me a horizontal stretch, so I don't want that. Instead, I want to put in the reciprocal of 1/2, so 1 over 1/2, as you know, that's the same as 1 times 2 over 1, which is 2. So I really want opposite of 2x in parentheses plus 4. So my function could be written as g of x equaling negative 2x plus 4. That should be our function. Let's take a look at what the graph looks like. Okay, so our original function was here in the blue, and that was the negative x plus 4. We can see the slope is negative 1, and we see the y-intercept at 4. And then our new function, which has been horizontally compressed, so all of these points were pulled towards the y-axis, and so we get this line here, which is our negative 2x plus 4. Same y-intercept as we were just talking about in that little hint, but the slope is now negative 2. It's a steeper line.
Well, sometimes when we do linear functions, we're going to involve more than one transformation, and we're going to apply the individual transformations one at a time in the order in which they are given. And that's important because you can get different answers. We're going to go with order that it was given. For multiple transformations, create a temporary function such as h of x, like we're going to see in this next example, to represent the first transformation, and then transform it to find the combination. Okay, so we're going to kind of do a step in between to help us work our way through. So let's look at this example. We're going to let g of x be a transformation of f of x equals 3x. So again, that's our starting point that we're going to use. Our ending point will be g of x. The transformation is going to begin with a horizontal shift of 6 units left. This will be followed by a horizontal stretch by a factor of 4, and then we'll want the final rule or equation for g of x. So step 1, we want to do the first translation, which is going to be to move to the left 4 units, or sorry, left 6 units. I'll just say left 6 here. So I'm going to just do a temporary one if I want here called h of x. It's going to kind of be my stepping stone to go from here. So to move left, if my original again was 3x, that means that I need to go in and add 6 units to the x value. So instead of saying just 3 times x, I'm going to take out that x, and instead I'm going to replace it by x plus 6. Again, that's my transformation from moving it to the left. I add to the x. Let's just clean that up a little bit before we get going here. So really I'm going to say that this first step is going to be the same as saying that h of x is equal to 3x plus 18. So transformation 1, that moved the original 6 to the left. Now let's go on to step 2, and we had another thing that we were asked to do in this case, which was asking you to take this one and horizontally stretch it by a factor of 4. So again, this one, the stepping stone, is the one we're going to use when we do that. So in order to move it or stretch it by a factor of 4, we need to remember what we just talked about. To horizontally stretch it by a factor of 4, we're going to replace each x with that 1 over b times x, where b is 4. So we're going to use the reciprocal of 4, which we know is just 1 over 4, or 1/4. So again, in our function here, instead of saying 3x plus 18, we're going to take out this x, and in its place, we're going to replace it with 1/4 times x. So this will become how we build our new function, g of x. So just cleaning that final one up a little bit, if I distribute that through, we'll get 3/4 x, and that 18 just stays as is. So g of x would be my final function here with both transformations combined.
Okay, and that brings up our last example. Example 4 is a fundraising application example. The golf team is selling t-shirts as a fundraiser. The function R of n equaling 7.5n represents the team's revenue in dollars, and n is the number of t-shirts sold. So from that function, we can figure out that they must be selling each t-shirt for $7.50. So that's why their revenue is going to be 7.5 times n, where n is the number of t-shirts. But the team paid $60 for the t-shirts, so you're supposed to write a new function, p of n, for the team's profit. So if we're going to figure out the profit now, p of n, we have to have our original revenue function, 7.5n, but we have to subtract off the cost of those t-shirts. So we're going to subtract 60 from that. All right, and then graph both p of n and r of n on the same coordinate plane. So that's here. So our revenue function was here, and then when we figure out, we have to have a shifting down of all of these points down 60 units, and we get our profit. Thank you, profit function here. So it's kind of interesting. We can see approximately when they actually start making a profit, right? Somewhere after they've sold the, was 3, 6, 9, somewhere around after they sold the 9th t-shirt, they will have made a profit. And what kind of transformation is that? Is that listed on here? describe the transformation that has been applied. So from our original graph here, what transformation? Well, this whole graph was just shifted down 60 units, so we would say that is a, a vertical shift down 60 units. All right, and that's it for this lesson. Thanks for watching, and we'll see you next time.
Have a good day.